So today we're going to talk about magnetic nanoparticles in cancer treatment, specifically in Theranostics, which means therapy and diagnostics. My name is Mahmoud Aga. I'm an undergrad at Zuhair University of Science and Technology, and today is May 14th, 2019. So we have the types of content that we are going to talk about today. We are going to talk about an intro, a fast intro to get us up and running with what the subject is about, and we're going to talk about what is it all about, the SPIONS in diagnosis and treatment monitoring. We're going to talk about therapeutics, how it is used in therapy. We're going to talk about also about the toxicity, the evil side of the SPIONS, and we're going to talk about translational research. So, the iron oxide Fa2O3. The iron oxide has great potential in oncological medicine, as they are, of course, biocompatible, biodegradable, easily synthesized, and easily functionalized, meaning that we can have a core of magnetite, which is the magnetic nanoparticles, and by then we can add more functionality to that core, thus incorporating it into something else that is more powerful. Okay, so we have a relation here which is stated that when we have spherical magnetite nanoparticles with diameter less than 20 nanometers, they will exhibit superparamagnetism, which is then exploited in contrasting magnetic resonance imaging. So we know that superparamagnetism is that super powerful magnetic attraction to fields that is exhibited by some materials, including the nanospherical magnetite nanoparticles, which are less than, of course, 20 nanometers. So, in order to make SPIONS, we need an iron core, which is the magnetic part, and a biocompatible or coating, that is the face that is going to see the wood. Like, we have a skeleton, the skeleton holds the body together, it holds it in shape, and then we have the skin, which other people say. So for the SPIONS, they have the coating that other molecules see, they interact with it, and also they have a targeting moiety. It just might mean like a key which they have, which might unlock some doors, which in this case is like cancer cells, which we need to unlock or to enter, we need to attach to in order to target these cells to see how effective the treatment is really going. So we have, as we said, a treatise of functionality for the SPIONS. We have first the iron oxide core, or the magnetite, which is the MRI contrast agent. We have it like we may use it as hypothermia therapy. We will talk about that in a minute. And we can also make it as a controlled drug release portfolio. We can also have a lot of functional moieties or ligands, like exactly functional moieties. We can have biotherapeutics, we can have polymer coating, we can have chemotherapeutics, we can have photofunctional moieties, we can have targeting moieties. Well, it depends on the kind of targeting that we need to do, the kind of cancer cells, or whether or not we are doing it for cancer cell, or like this is like a basic principle which can then be applied to other fields as well. So we have contrast enhancement nanoparticles that can selectively accumulate at tumor cells. This is the main function of the nanoparticles or the SPIONS. They are just simple contrast enhancements. They accumulate at tumor cells, thus increasing the resolution of the image, thus the tumor. We can see it better, we can know how to target it, we can know whether or not the treatment is fully functional without any invasive surgeries or any biopsies. So we have passive targeting, which is enhanced permeability and retention. Just means that we rely on other physical or physicochemical properties that surround the cancerous cells. We rely on physiological states that are exhibited there, that there is a lot of angiogenesis, which means blood vessel generation, and the blood vessels they are like wider than usual. We use that to target those cancerous cells. Of course, there are a lot of limitations to this technique. The limitations being that this is not exhibited by all tumors. Like, some tumors do not actually have that much angiogenesis, they don't have that much proliferation of blood vessels around the tumor. And of course, they are not homogeneous across the whole site. So one might get like a resolution, a picture, picture of the tumor, which would state that we have a very high concentration of tumor in one place, but very low concentration of tumor in another place. But that might not be the case, as we might have also have a big tumor at that other site that was shown to us that it was not that big because of the non-homogeneity of the passive targeting. To deal with the problems with the passive targeting, we have active targeting. So active targeting, in short, it means having a molecule that is like the key to target the cancerous cells. So we make the key attached to the surface of SPIONS. These keys or ligands can then recognize other biological structures. Another targeting method is magnetic targeting, which is using magnet. As they are all magnetic, we can use magnetic fields in order to draw them to the site of action and then do whatever we want. Like, I'll discuss what are we going to do with like magnetic nanoparticles in situ at the location of cancer. We can do a lot of damage to cancer cells, regardless or not they have a targeting moiety or a bioactive molecule that is going to disrupt the functionality of the cancerous cells. The limitation of the magnetic targeting is, of course, that it is not effective towards metastasis. Of course, metastasis needs we can't locate the cancer at one location. We have it spread out across multiple locations, and we can't just pinpoint at a place and say, oh, here is all the cancer that we need to eliminate and there is nothing else. We need to be more careful when it goes to metastasis. So we have an example, which is the TMZ, which is the current treatment for glioblastoma. We take chitosan nanoparticles that are covalently linked with DMZ, functionalized with pleurotoxin, which is a tumor targeting peptide. So this gives it much greater stability and targeting compared to non-targeted nanoparticles. Magnetic resonance imaging was also used to monitor the progression of tumors. So we have a chitosan peptide. We added a lot of functionality to it. We added the TMZ, we added the CDX, and then it was shown that it will have much greater stability and targeting compared to non-targeted NMPs, showing that the active targeting really increases the functionality or the targeting of the magnetic nanoparticles or the non-targeted nanoparticles. So we know that we have magnetic nanoparticles in situ. What we can do is do a little damage to them. We can use magnetic hypothermia or photothermal therapy, or we can use photodynamic therapy. So these all rely on disruption of the cell around them. So in short, they do a lot of damage just by moving around, wiggling, destroying some molecules, destroying some DNA here, destroying some RNA there. And we also have the photothermal therapy, which concentrates the energy in one place, thus bursting out the energy at one place. The photodynamic therapy works in a similar fashion, except that it must be located at a site that is near the cancer needs to be a superficial site. So of course it's not all good stuff, and we need to incorporate SPIONS next day in all of our research. We need to incorporate them in all of our medications. It's not all like that. So we, as humans, we have a maximum tolerated dose of 100 micrograms per milliliters. Other than that, we start to get into a lot of problems, including the disruption of cytoskeletons for the cells. They induce oxidative stress, they generate a lot of free radicals, and they impair mitochondrial function. They damage DNA and alter cell signaling pathways. So SPIONS actually can and will do a lot of damage if they exceed the tolerated dose that they are supposed to handle. So although the wide variety of SPIONS, they are not yet to be incorporated for humans, they are actually approved for treatment of humans. A lot of them are approved, but the approved formulations are no longer marketed. So we have a problem in incorporating these medications to a large scale market. We seem to fail to fulfill the dreams or the hopes of our customers. For this regard, we do not give the promised medical care that is to be expected from such promises on lab animals. So we still don't get that all the way. And also functionalized mRNA agents still don't exist for humans. And for the references,